All right, so what we're going to do now is look at resistors in series and in parallel. Now, our problems that we did earlier with the circuits, you could do the same approach for what we're about to do with resistors in series and resistors in parallel. But what's nice about series and parallel is that their behavior, how they function within a circuit allows us to take some shortcuts so that we don't have to do this whole outer loop and inner and right loop and all of that stuff we did. We're going to look at some equations there, and those equations are going to give us, just like those shortcuts that we could use rather than going through all these steps. All right, so let's look at resistors in series first. Okay. Okay, so let me tap here. Okay, so resistors in series. Okay, so if we have let me just set up a simple circuit here. Got your battery and two resistors. Okay, so pretty simple circuit here. This is some battery, some voltage. I'll just call it V. All right, let's start with a loop rule, okay? Because we've done a loop rule a couple times. We could do it again, and this is a pretty simple loop, but it's going to get to something that I want to show you guys. So here's my loop. Let's start here. Go around this way. All right, so the loop rule says that if you add up all the voltages in that loop, you should get a zero, or you will get a zero voltage at the end. So starting at that dot there, I had the voltage from the battery. Let me do a different color. Voltage of the battery, and then we have the two resistors. Now, my direction, I forgot to do directions here. So my current is going this way, and my direction for my loop, I'm gonna do this. Okay, so my direction for my loop and my current are the same. And if the direction for the loop and the current are the same, that means we're looking at voltage drop for resistors. Okay, so as we go around this loop, we get to the battery gives us a voltage gain. Get to resistor 1, we get a voltage drop. Get to resistor 2, another voltage drop. We know that it's going to equal 0. Okay. So let me use Ohm's law here. Ohm's law says V equals IR for resistors. So I times R1 minus I times R2. And notice that I did not put a subscript for I. There's a reason, right? I did not put a subscript for I because resistor 1 and resistor 2 always have this, are going to have the same current if they're in series. So that's actually one characteristic that I'm going to write here off to the side. Okay, so one of them is resistors in series always have the same current going through them. Okay, so they always have, we're not space there. So put that. Okay, always have the same current because of that junction rule that we talked about earlier. All right. So I'm going to rearrange this here. Let me rearrange these equations. So I'm going to call it, call it V battery. And I'm going to bring over the IR1 to their side and the IR2 to their side. Okay. Now, we're going to talk about this concept, kind of like we did with capacitors. We talked about this thing called equivalent capacitance. You have something with resistors as well. Resistors can have an equivalent resistance. And what that equivalent resistance is, let's say I have the same battery. Go back to the same color. I have the same battery, and I want to replace these two resistors with just one resistor. Call this R equivalent. And that R, and here's my battery voltage. That R equivalent is going to give me the same current as my other circuit. So I get the same exact current as the circuit on the left. Okay. So for the circuit on the right, if I'm getting the same voltage, same voltage for my battery, same current, this R equivalent has to have a different value than R1 or R2. And in this circuit, it's a pretty simple circuit. I hope you guys can see that the voltage here in the battery is the same voltage as R equivalent, right? They're just connected to each other. So the voltage gain here is going to equal the voltage drop here. Okay. So using this circuit, and if you want, you could set up the loop law, but I don't think you need to. Using the circuit, I can make a substitution for V battery. I'm going to make V battery I, same current, times R equivalent. Okay. So I use this idea of equivalent resistance, right? What equivalent resistor does is it keeps the same current in the circuit by replacing those two or more other resistors. Okay, so it keeps the same current there. So that's why I keep this as I. Right? You see I, so I here, I here, I there. So I have I's and they're all the same I's, so they cancel out, and I get this equation for equivalent resistance for series. And if we had more resistors in series here, you just keep adding them. Okay, so this allows us to find the equivalent, my equivalent resistance, or if you want to say total resistance, although I kind of have an issue with that. My equivalent resistance in a circuit with series resistors. Okay, so let's do one example with this. Okay. So I'm going to do a simple example with this. Oh, you're welcome. Okay, so I'm going to have a 20-volt battery here and 2 light bulbs. Battery, 2 light bulbs here, 10 ohms. And this resistor here would be 5 ohms. Okay, so that's the circuit I'm dealing with. So what I want to do with the circuit is find the total current coming from this circuit. Okay, so let me write that here. Find the current supplied by the battery. All right, so there's a couple things we don't know. If we're definitely going to use Ohm's law at some point, right? V equals IR. Okay, so we're going to use, go here. But here's the issue. You don't know, just by looking at this, or maybe you do if you know how to use the ratios, but let's say you don't. You don't know the voltage across a 10 ohm resistor, and you don't know the voltage across a 5 ohm resistor. So Ohm's law there would only work, to find current, would only work if you knew the voltage across those specific resistors. The 20 volts, that 20 volts gets split up between the 10 ohm resistor and the 5 ohm resistor. Okay, so and that's where I said the ratios will come in handy. But let's say I'm not going to solve it through the ratios. So what we can do is if I can use a 20 volts here, so I can make this the voltage of the battery if I'm using my equivalent resistance. Okay, so if I'm using my equivalent resistance in Ohm's law, then I can use the voltage of my battery. If I'm not, then I would need to know what's the voltage across each specific resistor. Okay, so let's find the R equivalent here. So R equivalent for series, come on, it's just R1 plus R2. So in this case, 10 plus 5. Okay, so 15 ohms there. And once we get our resistance, our equivalent resistance, we can use that to find the current. So current equals voltage over R. Now, which voltage are we going to use, and which resistance are we use? If we use the equivalent resistance, then we can use the voltage of the battery. Okay, because going back to this picture up here. Let's see. Going back up to this picture, this is kind of what R equivalent does. R equivalent takes whatever circuit we're looking at and reduces it to just one resistor. If that's the only resistor we have in our circuit, then the voltage of your battery is the same voltage across this equivalent resistance. Okay, so hope that makes sense to you guys. Voltage, so I'm going to use my voltage of the battery over my R equivalent, which is 20 over 15. Okay, and that gives you 1.33, so which is 1.3 amps. Okay, so that is how we use our equivalent resistance there. Now, what would happen to the circuit? This is an additional question, so kind of I solved the question here. But what would happen to the circuit if I took out one of those resistors? What do you guys think? So what happens? So these are, let's say these are light bulbs, right? Light bulbs are supposed to be giving off light. Okay, giving off light. What would happen to the light bulb if I took out, let's say, the 10 ohm resistor? Would the 5 ohm resistor still light up? By take out, I mean, I don't, I mean something like this. Oops. Well, that's pretty much going to answer the question. Okay. Okay, so if I took out the 10 ohm and didn't connect it, right, this light bulb, this 5 ohm light bulb would not turn on. If it was connected, the light bulb would be brighter because that would mean more current, you know, going through the circuit. But if it wasn't connected, if I just take out one light bulb, then the other one won't light up. Okay, so this is what happens when you have light bulbs in series. If one of them shorts out, or you know, something happens to it so that it's not a connection anymore, the rest of the light bulbs in that chain or in series with it are not going to light up. Yeah, you know those crystal lights, you get the way the crystal lights though, they have several circuits in those lights, different parallels. So you'll have like a chunk of crystal lights that all turn off. Other ones won't. Some of the other ones will turn on, but you have a chunk of crystal lights that turn off, and I go, okay, great. Now to find out, you know, where those, which light bulb actually was burnt out. So, you know what's weird about crystal lights too? I'm going off topic. That you put them away so gently the year before, and then when you pick them up again, thinking that okay, I was gentle with them, nothing happened. There's always just like for some reason a couple that don't turn on. Anyway. I'll stop railing on Christmas lights. All right, so I'm not generally mad on that. Yeah. Part of the seasonal experience, I guess. let's look at resistors in parallel. Okay, so again, we looked at this with capacitors. So there's a lot of similarity with what we saw in capacitors versus resistors. But let me just go through it again. Okay, so resistors in parallel. So a parallel setup will look something like this. So let me make one longer. R1, R2. And this is some battery with some voltage V. Okay. All right. So in this case, I'm going to draw this a little differently. I have a highlighter here. All right. So I want you to think about what's going on with a voltage in the wires. Okay. So I'm going to have a, let's see here. Okay, so for the top wires here, where all those wires connected together, we're going to assume that the wires have a very, very low resistance or zero resistance. So they're all going to maintain the same voltage. So for the top here, these are all at the same voltage, right? There's no resistor there. Voltage doesn't change. So whatever voltage the battery's at, that's a voltage across the top wires. On the bottom wire, well, the bottom wires are connected to the lower voltage, right? We usually say it's zero voltage there. So it's zero voltage here, let's just say. And that means all the wires connected to this are also held at zero voltage. So I'll do it like this. Oops. Okay. So the red is at a certain voltage, 20 volts, let's say. The blue is at another voltage, 0 volts. What that tells you, just by analyzing that way, is that the voltage across R1 equals the voltage across R2. So that is a characteristic of parallel setups. Setups here, or resistors in parallel, whatever you want to write. So voltage is the same for resistors in parallel. And it doesn't only apply to resistors. I think we saw the same thing when we looked at capacitors, right? Capacitors, if you put capacitors in parallel, they also have the same voltage. Okay, so we have that that characteristic, which we're going to use in a second. And you would see the same thing if you did your loops, right? If you did one loop for the, let's say, the left loop, and then you did the outer loop, you can conclude through using the loop law that voltage of R1 equals a battery, and voltage for R2 equals a battery. Okay, so you will get the same thing through loop laws, but I think my little drawing here is a little bit better, a little bit easier, definitely quicker. Okay, so let's talk about currents. So current, I have current going through here. We hit a junction right here, so it splits. I get I2 going this way, I1 going this way. Oh, I1. Okay, so the current splits up. They are not necessarily going to be equal. The only way those two currents could be equal is if the resistors are equal. But let's assume they're not. So these are different resistors. And so I1 will not equal I2. So they have different currents going through there. Okay. All right. So, but I could use the junction rule. Let's see. Junction rule says this. Right, I1 plus I2. That's the junction rule we got earlier. And I'm going to use Ohm's law here. So I'm going to substitute for my I's V over R. So this would be V over R1. And that V is the voltage of the battery, plus I2 is going to be V over R2. Okay, and we're going to do something really similar to what I did before, where if I had a equivalent resistance, so I took these two resistors and substituted one resistor, or equivalent, such that I get the same current going through here, same total current going through that. Then for my I will substitute this V over R equivalent. Okay. So you can see what's going to happen with the algebra there. All those V's, the voltage of the batteries, are going to cancel out, and I get an equation for resistors in parallel. So that equation is 1 over R equivalents equals 1 over R1 plus 1 over R2. And if we had more resistors in parallel, you just keep adding them. Okay. Let's see here. So I'm not going to do an example for resistors in parallel because it'll be really similar to what we did last time. I will do another example that has parallel and series together, but we won't do one for parallel. Okay, so I wanted to ask kind of the same question. If I removed this one here, well, let's say I remove R2, so that my circuit looks like this now. This is still R1, this is still V. Would R1 still have current? Or if these were light bulbs, would the light bulb for R1, would that light bulb still light up? Yeah, okay, good. All right, excellent. Okay, so yeah, it would, because you still have, if you look at the circuit, you still have a complete circuit here, right? You still have current flowing through and going back. So this is not a short circuit. It's not an open circuit. It is a complete circuit. So, or what we would say, a closed circuit. So yeah, this with parallel setups, you could remove a resistor or light bulb, whatever the case, and you still have one turning on. Or you still have the other ones turning on. All right, maybe another question here. This one's a little trickier. Let's say I added more resistors. So let's pretend these are light bulbs. I didn't draw them as light bulbs. Right? That's not how you draw a light bulb. But I don't want to go back and erase it. These are let's say these are light bulbs. As I keep adding more light bulbs into my circuit, what's going to happen to their brightness? Okay, get less current, therefore they get dimmer. Okay, so let's see. Well, let's take a look, because there's something that contradicts that. Remember we looked at the what's going on with the voltages. Here's the voltages, right? All these are going to be the same voltage. Those are all the same voltage, and same thing on the bottom. These are all connected to the same voltage. All right. So if I solve for current, oops. Where is it? If I solve for current here, current is voltage over resistor. Well, my voltage isn't changing, right? As I keep adding more and more and more resistors there, that V stays the same, no matter how much more resistors I add. And if that V stays the same and my R, let's assume they're all the same. If the R is staying the same, then I get the same currents going through there. So this current I have up here is not going to be any different than the current going through to here. Okay, so I still have the same currents, I1, going through this light bulb than I did initially. Now, what that means is, I have I1 here, is that the current supplied by the battery really has to go up, right? That current, the battery is supplying current, not just for this light bulb, right, but supplying current for this one, for this one, for this one, for this one. So that battery has to supply a lot of current. And what we're going to talk about next time is that batteries, once you have a lot of current running through them, they don't act as efficiently. And so realistically, you can't really have a light, using a real battery, you're not going to have these light bulbs all staying the same brightness. Okay, but if we assume an ideal battery, a battery that has no what we call internal resistance, then all these light bulbs will stay the same brightness, or we'll keep their brightness the same as you connect them in parallel. A little trippy, right? You would think that they would get smaller and smaller and smaller. In practice, they do, but theoretically, they don't. Okay. So I have one example to do, and then we'll call it a day here. Okay. Series parallel example. So I'm going to set up a circuit, and we are going to solve this circuit. Okay, I should make that a little clearer. Okay, so here's my battery. I'll make this, just make it 10 volts. And I'll make these resistors, let me label these resistors as well. So I'll call this R1, 5 ohms, 2 equals 10. And R3 down here also equals 10. Okay, so there is my circuit, and I want to find the voltage. All right, so that's what we want to do. All right, so when we look at a circuit like this, we got to determine what resistors are in series, what resistors are in parallel together. So I think it's helpful if I do those color things I did earlier. Okay, so we have a certain voltage coming from the battery, 10 volts. That 10 volts, different color. Okay, so in the red, that's 10 volts. It hits that resistor drops my voltage. Okay, so now it drops my voltage to, I don't know, a different voltage. So now I have a different voltage here and here, right? Because those two are connected by that junction. They hit resistor 3 and resistor 2, and then we get a final voltage down here. Okay, so so drawing that, hopefully you can see which resistors will have the same voltage drop. You can see that we have green to blue for R2 and for R3. Okay, so what that tells us, if they have the same voltage drop, just like that, so R2 and R3 are in parallel to each other. Okay, they have the same voltage drop, so we say they're in parallel to each other. And then if you look now at R1, R1 is in series with, now, so R1 is in series not with just R2 or R3, but it's in series with R2, let me say what you say is, let me say it this way, with the equivalent capacitance, or resistance, I should say, resistance of R2 and R3. Let me show you what I mean by that by drawing another circuit. So let's say I combine R2 and R3. This is R1. So if I draw like that, you know, I take R2 and R3, combine them together, and here I'd redraw the circuit. Hopefully you could see that R1 and R23, my equivalent capacitance for R2 and 3, are in series together. All right, and even then, I could take R1 and R23 and combine those. You get R equivalent. Okay, so what I want to do here in order to get current, I know my voltage, right? My voltage is 10 volts. If I could find R equivalent, then I could find the current supplied by the battery pretty easily using Ohm's law. So the task here is to find R equivalent. Okay, so let's go back at R23. R23 is a combination of these two, right? R3 and R2, both of which are in series, or not series, are in parallel together. Okay, so if these are in parallel and we want to combine them, we saw earlier that the resistance, or the equivalent resistance for parallel, is so 1 over R23 equals 1 over R2 plus 1 over 3. Okay, that was our equation for equivalent resistance for parallel, right? You add the inverse of them. So if you do that, I'm pretty sure you get 5. Yeah. Okay, so I have my 5 ohms here. R1 is 5 ohms as well. Okay. And now I can see R1 and R23. To get my R equivalent, and we're adding up R1 and R23. Like I said, they're in series. So in order to add those up to get R equivalent, well, they're in series. So series, you just add those two resistors. Okay. All right, and we just get 10. Right. The way we get 10 is to do 5 plus 5. Right. Okay, so we got my R equivalent there. This R equivalent that I have down here. 10 ohms. Okay, so the battery is 10 volts. My R equivalent is 10 ohms. And now I can use Ohm's law. Ohm's law is I equals V over R. So 10 volts over 10 ohms gives me 1 amp. Okay, so that is the current supplied from the battery. All right, so I answered part of the question. Current supplied by the battery, 1 amp. Now we've got to figure out what's the voltage across R2. All right, let me go back to this picture here. This picture here. Let's think about what's going on with the voltages. I know I have 10 volts here in the battery, right? The battery is supplying 10 volts. Put that in. I'll put this in blue, I guess. $10 volts. What is the voltage drop across R1? So we could, again, use that finding Ohm's law, right? We know the current here that's being supplied from the battery is 1 amp. Right, that's what we just calculated, and that on the bottom of your screen there. So the voltage drop across resistor 1 using Ohm's law, right, V equals IR, which would be 5 volts. Okay, so I have a voltage gain, 10 volts from my battery, a voltage drop, 5 volts from resistor 1. What would be the voltage drop for R23? And you could figure that out a couple ways. We could do Ohm's law again, V equals IR. 2 resistors in series always have the same current. So that 1 amp, this 1 amp here, this 1 amp applies to the R23 as well. So I times R gives you 5 volts. Or you can also see that if you go in a loop, you have to get 0. That means the voltage drop here has to be 5. Okay, so this is going to be 5 volts here. Okay. Does that give me my answer? Voltage across R2. Well, it kind of does. The voltage, I got my voltage across R23, which is referring to these 2 resistors. What do 2 resistors in parallel have in common? 2 resistors in parallel have in common voltage. So if we got 5 volts here for the R23, that means it's 5 volts across R2 and 5 volts across R3. Okay, so which gives me my answer. My voltage across 2 is also 5 volts. So that was my answer here. This is my answer down there. Okay, so we're in these problems. What we're doing is taking these resistors, finding the equivalent resistance by combining as much as we can, and once we find the equivalent resistance, we use the characteristics of series and of parallel, right? And I did that earlier. When did I use the characteristic of parallel or series? I use that characteristic right here in order to explain that this current, this resistor feels the same current as this resistor. So both feels the same current. So that was a characteristic of series. And then I use characteristic of parallel to explain that whatever voltage I have here is the same voltage I have in these 2. Okay, so the reason why I'm rehashing that is because the equations on their own, right? Equations for Ohm's law, the equation for resistance, equivalent resistance in series and equivalent resistance in parallel, those equations won't help you get your final answer. You have to know the characteristics and apply them in your problem in order to get their answer. Okay, so we'll stop there. We'll look at another example when we come back and finish chapter 28 in our next class. And then we'll also look at RC circuit. So we're going to put a resistor and a capacitor together and analyze that. All right, so till next time.